Transformation lesson part 2. On the next few examples, we're going to practice writing the motion rule. The red triangle is the pre-image, where the blue triangle is the image. In other words, red is new, so red is old, and blue is new. So our job is to figure out how you went from old to new. So to do that, let's go and take a look at point to point what happened between each point. So start with A. To get to the from A to A prime, first you went left 5 units, and then you went up 3 units. Okay, let's investigate B. Left 5 units, up 3 units. So far, it seems to be a trend. Let's just be sure. C, you go left 5 units, and again, up 3. So when you write the motion rule, it looks like an ordered pair, where you're going to have your X and your Y, but you're also going to add some operations and numbers to represent your movement. So since my X's went left 5 units, that my X values decreased. So to show a decrease, we need to use subtraction. So my X is subtracted by 5. For my Y values, since I went up, that's an increase. So my Y values increased by 3, so I add. So that's one way to write the motion rule. You could also write it in vector notation, where vector notation has like a strange bracket, and they just put the numeric value. So it would be -5, 3. So you need to familiarize yourself with both ways of writing a motion rule for a translation. Underneath the Statue of Liberty example, write down this example, the motion rule. You probably need to redraw the picture and snap a photo. Now we're going to talk about lines of symmetry or line symmetry. A line of symmetry is a line that you could draw from vertex to vertex or from edge to edge, and you should be able to fold the figure on that line and produce mirror images where they should fold over and no edges stick out, or they should match up totally from 100%. So for example, I could take this square and cut it down from edge to edge and fold it along that dashed line, and that's one line of symmetry. I could fold it horizontally as well, and that's the second line of symmetry. I could fold it at the diagonals, and that's a third line of symmetry. And I can fold it at this diagonal. That's a fourth line of symmetry. So that one square has 4 lines of symmetry. Let's go look at the diamond. I could fold it here. That's one line of symmetry. I could also fold it here. That's another line of symmetry. If I tried to cut it from edge to edge, the edges would, or sides would not match up exactly. So this diamond only has 2 lines of symmetry. When I look at this parallelogram here, I could fold it on the diagonals, and it should line up edge to edge. So that's one line of symmetry. And I could fold it along this diagonal, and it should line up edge to edge. So that's 2 lines of symmetry as well. Now for this triangle, it has no lines of symmetry, because if I go from this vertex here, those 2 sides are not the same. They have to be completely identical. So in that, therefore, the triangle has no lines of symmetry. It is possible for a figure to not have a line of symmetry. A glide reflection. A glide reflection is a combination of a translation and a reflection. So in this example, they would like for us to first translate it using this vector rule, 0 to -2, and then reflect it across the y-axis. Sometimes your textbook or a question might, instead of using the word across, it might say reflect in. It means the same thing. It's just tomato, tomato. So the first thing I want to do is give each point a letter. So let's say this is A, this is B, and this is C. So A is located at -4, 8. B is located at -4, 5. And C is located at -3, 5. Now, according to the translate vector, my x's will not change. However, my y's will decrease by 2. So my a prime, my x would be the same, so -4, but my y's decreased by 2. So 8 divided by 8 minus 2 would be 6. For b prime, again it stays -4, but my 5 will decrease to 3. And c prime, -3 would stay the same, but the 5 would decrease to 3. So here's the new figure after the translation. Each point goes down 2. So here's my new triangle. Now we need to reflect in the y-axis. The y-axis and your y's run vertically, so your y-axis is this red line here. So now we must ask ourselves, how far away is each point from the y-axis? And that'll tell you where your new point will be located. So if I look at B, B is 1, 2, 3, 4, 5, 6, 7. Whoa, sorry, something's not right. My ordered pair is totally not right. Hold on. I put -4. It was 1, 2, 3, 4, 5, 6, 7. Sorry, my mistake. I need to fix those. This is not right. Those aren't right. That's not right. That's not right. Alright. It's -7. -7. -7. -7. So my A is 7 units from the y-axis. So A double prime will also be 7 units from the y-axis on the other side. So 1, 2, 3, 4, 5, 6, 7. Here would be A double prime. Same thing for B. There's B double prime. Now C is only 3 units away from the y-axis, so that means C double prime will also be 3 units from the y-axis. So here would be the reflected triangle. And this would be the final image. So A double prime is positive 7, 6. B double prime is positive 7, 3. And C double prime is positive 3, 3. What you should have realized is that when you go across the y-axis, your x's change their signs. Your y's will stay the same. That is the rule. When you go across the y-axis, your ordered pair will map just like this. X's will change signs. So that's why we say negative x. In other words, change the sign. But your y's will stay the same. So if you're a rule-based person and can remember that rule, that could cut you some time. This is the rule for when you reflect the y-axis only. This is just another practice with glide reflection. Work on this one and take a picture. Now, for this one, I'm going to work it out with you. I believe it's the same triangle as before, the same ABC coordinates. So I can write down those coordinates again. A was at negative 7, or positive 8. B was at negative 7, 5. And C was at negative 3, 5. Now, for the first translation, they want us to add 3 to your x's and your y stay the same. So it would be negative 4, 8, negative 4, 5, and 0, 5. So let's redraw that picture. Negative 4, 8 would be here. So that's the translation. Now they want us to reflect over the line x equals 2. X equals 2 is that dashed line there. So it's a vertical line. We're not reflecting over the x or y axis. So there isn't a hard, fast rule for this one. So you're just going to have to know how many units away from the line the triangle is. So when I look at A prime, it is 1, 2, 3, 4, 5, 6 units away from x equals 2. So 1, 2, 3, 4, 5, 6 units away would be A double prime. And the same thing for B double prime, also 6 units away. And C happens to be 2 units from the x equals 2 line, so C double prime will also be 2 units away. So here would be the final image. Rotations. When it comes to rotating, you need to know these two things. Order, the number of times you can rotate to get where you started, and the magnitude, number of degrees for the rotation. So the order, how many times can you rotate? The total number of rotations. And the magnitude will be how far did you turn it to get that rotation. Side note, the order times magnitude will equal 360 degrees. Always, always, always. So now we're going to discover the order and the magnitude for various shapes. So let's find out the order of this shape here. So this is the first way that the shape appears. This is 0 degrees. So if I rotate it 90 degrees or start rotating it to the left, right now it's not quite exactly the same. But if I complete the 90-degree rotation, let's assume this is the square. So at 90 degrees, it looks like exactly where I started. So that was one rotation. All right, let's go around again. Oh, that's 180 degrees. That was 2 rotations. That's 270 degrees. That's 3 rotations. And back to where I started, 360 degrees. That's 4 rotations. So the order for this one would be 4. And the magnitude was 90 degrees. Every 90 degrees, the figure looked exactly the same as it initially did. Every time we turned it counterclockwise, the figure looked exactly the same. So 1, 2, 3, 4. All right, let's practice one more. Let's take this figure. This is the original location with the star being on the right. How long will it take to get, how many times can I turn it around before it ends up back at that spot? So here's 90. Nope. Here's 180. Nope. There's 270. Nope. And there's 360. So I had to go full circle before I got a rotation. So the order would be 1, where the magnitude is 360. So I guess it's safe to say that this does not have rotational symmetry because you have to totally go 360 degrees in order to land in the same spot. So this is not a special shape with rotational symmetry. And this concludes your lesson for today.